Welcome back, Focus Learners. Let's jump right into today's explainer because we're going on a journey that absolutely blows my mind. We're taking a trip from the most extreme, mind-bending theoretical objects in the far reaches of the universe straight into the high-tech, high-performance engineering that's illuminating the very room you're sitting in right now. We're talking about the physics of total control, how mastering the smallest particles known to science, from quarks to photons, is completely redefining the limits of both cosmic evolution and modern industrial progress.
Okay, let's dive right in. Here's our roadmap for this explainer. Number 1, limits of extreme matter. Number 2, inside the quark star. Number 3, magnetism as a cosmic force. Number 4, high-tech photonics with QuarkStar LLC. And finally, number 5, progress through total control.
Section 1. Limits of extreme matter. The Bodmer-Witten hypothesis. To really understand total control, we first have to understand what happens when standard matter completely breaks down under unimaginable pressure. Normally, quarks, the fundamental building blocks of protons and neutrons, are locked up tight. But the Bodmer-Witten hypothesis suggests something wild. If you apply enough pressure, pressure that way exceeds the density of an atomic nucleus, matter might actually transition into a new, completely stable state called strange quark matter. By adding a third, quote-unquote strange, flavor of quark to the usual up and down mix, the quarks can occupy a whole lot more quantum states. This drops the Fermi level and reduces the overall energy, creating a state that's actually more tightly bound than ordinary elements like iron. It fundamentally redefines our entire understanding of what matter can even be.
To put this into perspective, think about the number 0.77. There's an object out there in the supernova remnant, Hess J1731-347, with a mass of 0.77 times our Sun. But here's the kicker. All of that mass is packed into a radius of just 10.4 kilometers. For standard stellar physics, that combination of low mass and tiny radius is a massive headache. Standard nuclear matter would demand a much larger radius. But for a self-bound strange quark matter model, it fits perfectly. It's honestly one of our best prime candidates for a true quark star.
So how does a wild, extreme object like this actually come to be? Well, it usually happens in one of two ways. First, a massive star collapses during a Type II supernova. Or second, an already existing neutron star pulls in extra mass or maybe slows its rotation. Once a very specific density threshold is crossed, the quarks literally deconfine. They break completely free from their proton and neutron cages. And this triggers what's known as a Quark-Nova. This crazy transition releases an absolutely immense amount of binding energy, which could potentially explain some of the bizarre, highly energetic radiation bursts we sometimes see lingering long after a supernova event.
Section 2. Inside the quark star. High details of quantum liquids.
We've seen how they form, so let's peel back the layers and look at the highly detailed quantum mechanics happening inside the core. The inside of a quark star isn't just some chaotic, messy soup. It's actually a highly structured quantum liquid. At ultra-high densities, the strong nuclear force actually becomes attractive, causing quarks to pair up, kind of like how electrons do in a superconductor. This leads to the absolute most stable phase at these densities, the color-flavor-locked, or CFL phase. In this state, there's a perfect symmetry between the three colors and three flavors of quarks. The result? The core acts as a perfect baryon superfluid, meaning it flows without any friction whatsoever. And it's a complete electromagnetic insulator. It is literally the universe's ultimate display of structural order.
But what happens right at the surface? Okay, prepare to have your mind blown here. The transition from that ultra-dense quark core to the vacuum of space is one of the most abrupt boundaries in all of nature. The quark density drops to 0 over a distance of just 1 femmeter. That's 10 to the power of -13 centimeters. Because electrons aren't bound by the strong force, they spill out just slightly past the quarks, creating this charge-neutralizing skin called the electrosphere. This razor-thin boundary generates a staggering electric field of 10 to the 18th volts per centimeter. This field is so unbelievably strong that it can actually levitate a thin crust of normal nuclear matter over the star, supporting the whole thing without the two ever even touching.
Moving on to Section 3. Magnetism as a cosmic force. Spontaneous field generation.
Remember that staggering number, 10 to the 18th power? Well, it doesn't just apply to the electric field. It also applies to the internal magnetic field in Gauss. For some context here, Earth's magnetic field is about half a Gauss. A quark star can generate a field of a billion Gauss. How is that even possible? It's through a process called color ferromagnetism. Inside that dense quark plasma, a color magnetic field is generated spontaneously. And since quarks carry both color and electrical charge, their interaction with this internal field creates this massive, macroscopic magnetic field.
Now, you can't just have a magnetic field that intensely powerful without it completely tearing the star apart. To maintain stability, the star requires a very specific geometry called a twisted torus. A purely polyidal field, think of the field lines running straight pole to pole, would squash the star flat. A purely toroidal field, running around the equator like a belt, would stretch it out like a cigar. Both of those are highly unstable, but by mixing them, storing roughly 90% of the energy internally in the toroidal field and 10% in the polyidal field, the star achieves perfect, stable equilibrium.
And you know, this brilliantly illustrates the main theme of our explainer, how total control over fundamental physics yields extraordinary stability and power. But here's the twist. This concept isn't just limited to deep space. On one hand, we have the cosmic scale, controlling deconfined quarks and Fermi pressure. On the other hand, we have the grounded, practical microscale, right here on Earth, controlling photons and pushing the absolute limits of Haitz's law, which is basically the LED equivalent of Moore's law. This brings us to a remarkable high-tech company that actually shares both a name and a philosophy with our cosmic phenomena, QuarkStar LLC. Section 4. High-Tech Photonics, QuarkStar LLC. The physics of total control on Earth. Let's transition from theoretical astrophysics to high-tech industrial photonics. This is where scientific progress translates into massive real-world successes and incredible added value. QuarkStar LLC was founded by absolute pioneers of solid-state lighting, including Roland Haitz. Their core philosophy? The absolute control of the photon from the exact moment of its creation to its final target. This integrated system of lighting, or ISL, represents a huge leap in added value for the industry. By using innovations like EdgeX modular extractors to perfectly shape light without any harsh glare and these ultra-thin 2D light sheets, they're treating lighting not just as a bulb, but as a high-tech architectural material. They are literally controlling photons with the exact same precision the universe uses to organize quarks.
Remember that recurring motif of magnetism we saw out in the stars? Well, QuarkStar uses it too, right here on Earth. To achieve truly modular, flexible environments, they utilize wireless power transfer via 150 kHz magnetic induction. This completely isolates the lighting fixtures from the AC grid. There are 0 physical wires connecting the light to the power source. This is a massive leap in high-tech progress, offering huge gains in both electrical safety and overall efficiency for modern smart buildings.
Building on that induction technology, they also use physical magnets for mounting their wireless fixtures right to ceilings. Their overarching vision is perfectly captured by this idea: the fixture becomes as adaptable as the light it produces. It's a real game changer. It represents a final revolution in lighting infrastructure. By blending mechanical engineering, magnetic mounting, and pure photon control, QuarkStar has achieved a level of adaptability and efficiency that fundamentally redefines what a light fixture even is.
Which brings us to Section 5, Progress through Total Control, Converging Scales of Science.
So what do a hyperdense stellar remnant and a cutting-edge LED lighting system actually have in common? Let's bring both halves of this explainer together. When we lay these concepts side by side, the structural parallels are honestly fascinating. In a quark star, the primary particle is the deconfined quark. At QuarkStar LLC, it's the photon. Magnetism stabilizes the star through color ferromagnetism, while on Earth, magnetic induction powers and mounts the lights. The efficiency of the star comes from strange matter's binding energy, mirrored exactly by the extreme efficiency of specialized optics, like compound parabolic collectors in the LEDs. And the ultimate goal for both? Maximum density and extraction, just maximum efficiency across the board.
And this drive for absolute efficiency leads to an incredible convergence in miniaturization. Out in space, we face the missing pulsar problem, where extreme matter-light interactions might actually allow tiny, super-dense quark stars to mask themselves as black holes. Back on Earth, QuarkStar's continuous further development of advanced light sources aims to shrink the entire distribution system of a massive luminaire down to the size of a single microscopic package. Both realms represent the absolute physical limit of what matter and light can become before collapsing into singularities or atomic-scale packages.
Moving forward, the ultimate test for these two frontiers are remarkably clear. For astrophysics, as gravitational wave detectors get more sensitive, the goal is to detect magnetic love numbers, which is the specific way these stars deform under magnetic tidal forces to finally prove their existence beyond a shadow of a doubt. For industrial photonics, the test is the continuous expansion of deep tech patent portfolios and delivering real-world, highly profitable efficiency through products like their Equinox fixture.
Which leaves us with this final awe-inspiring question to consider. Whether it's a magnetar shining in the deepest, darkest corners of the cosmos, or a dynamically controlled LED illuminating a museum wall, the underlying physics of extreme control remain exactly the same. Will mastering the most fundamental forces of the universe, literally dictating the behavior of single quarks and single photons, be the ultimate benchmark of our technological progress? I'll let you ponder that the next time you turn on a light. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.